In this video, we're going to talk about the importance of the second derivative when it comes to um, graphing. And specifically, we're going to talk about concavity and points of inflection. First of all, let's talk about what it means for a curve to be concave up, or in other words, for the second derivative to be greater than zero. Imagine we have the curve shown right here in black. We see that on the left part of the curve, the tangent is negative, and then in the middle, the tangent is 0, and then to the right, the tangent has a positive slope. So the slope, as we move from left to right, is going from a negative to a 0 to a positive. In other words, the rate of change, a positive. So in other words, the rate of change of the slope is positive. The slopes are going from negative to 0 to positive, so the rate of change of the slope is positive. Well, slope is another way of saying rate of change. So instead of saying the rate of change of the slope is positive, let's say the rate of change of the rate of change is positive. Well, if I say if rate of change means first derivative, then rate of change means second derivative. So when you have a curve that looks like the one that we drew here in black, that I'm now tracing over in red, when you have a curve that looks like that, the second derivative is positive, and we call that concave up. Now, what if we have concave down? Well, let's take a look at this. The black is the function, and we've got a first derivative that's positive, and then we've got a first derivative that's close to 0, and then we've got a first derivative that's negative. So our first derivative goes from positive to 0 to negative. So as we move from left to right, the slopes are decreasing. If something goes from positive to 0 to negative, it's decreasing. So moving from left to right, the slopes are decreasing. Another way of saying that is the rate of change of the slopes is negative. Well, slope means rate of change, so we can say the rate of change of the rate of change is negative. Well, if rate of change is first derivative, then rate of change is second derivative. So we can say the second derivative is negative instead of saying the rate of change is negative. So the short thing to remember is that when a curve looks like this, the second derivative is negative, and we say it's concave down. So we can now develop what we're going to call a second derivative test. If we've got a first derivative equal to 0, but it's in a region that's concave up, then there will be a local minimum. Concave up means second derivative is greater than 0. So if we've got the first derivative equal to 0 and the second derivative greater than 0 at a certain point, that's a minimum. Similarly, if we've got a first derivative equal to 0 at a certain point, but the second derivative in that part of the curve is negative, in other words, it's concave down, that'll be a local maximum. Now, there are times where a tangent line, the placement of it will change significantly moving from left to right. And specifically, what we're going to say here is sometimes the tangent line is above a curve and then becomes below a curve, or vice versa. So right here, if you look at this point right here that I'm indicating in red, we've got a tangent line. If we draw a tangent line to the left of that, it'll be above the curve. But if we draw a tangent line to the right of that, it'll be below the curve. Notice how at that point, the tangent line goes from one side to the other. That's a point of inflection. We went from a curve that was concave down to a curve that was concave up. Point of inflection, and specifically f prime prime of x is equal to 0. It can also happen the other way. So notice on the right diagram, we've got a first derivative that's negative, and then it's also negative on the other side. But on one side of that point, the tangent line is below the curve. On the other side, the tangent line is above the curve. We're going from a part of the curve that's concave up to a part of the curve that's concave down. So that point at which it occurs is called the point of inflection, and the second derivative is equal to 0 at that point. So if we put it together, we have times where the first derivative is greater than 0 and the second derivative is greater than 0. That means that the function itself is increasing and concave up. Sometimes we have a first derivative greater than 0 and a second derivative less than 0. Well, the first derivative being greater than 0 means it's increasing, but the second derivative being less than 0 means it's concave down. And the curve will look like the second one right here, the one I'm pointing at. What if we have a first derivative less than 0 and a second derivative greater than 0? Well, this means we have a decreasing function, but this second derivative being greater than 0 means it's concave up. That curve is going to look like what's shown. And finally, if both first and second derivative are less than 0, then we've got a function that's decreasing and concave down. It's going to look like this right here. So suppose we want to use our knowledge of first and second derivatives to graph the curve y equals x cubed minus 3x squared minus 9x plus 10. First thing we're going to do is determine the first derivative, and we're going to set it equal to 0. So 3 times x plus 1 times x minus 3 will equal 0. So we'll see that y prime equaling 0 means x is negative 1, or x is equal to 3. So these will be critical numbers for us. Now, we're now going to determine where y prime prime is equal to 0. Well, if y prime is 3x squared minus 6x minus 9, y prime prime will be 6x minus 6. So if 6 times x minus 1 is 0, then that means x equaling 1 will be the point at which the second derivative equals 0. So we've got the first derivative equaling 0 at x equals 1 or x equals 3, and the second derivative equaling 0 at x equals 1. Now, we're going to do something pretty cool here. We're going to set up interval testing, one on top of the other. The first one will be with the second derivative, and the first one will be with the first derivative. The second one will be with the second derivative. Now, when we do interval testing on the first derivative, the critical numbers are negative 1 and 3, so we indicate those on the number line. And we do our pretty standard interval testing. We pick a number to the left of negative 1, and when we do that, we see that this first derivative is positive, and then we pick a number in between negative 1 and 3, and when we do that, the first derivative is negative. And finally, we pick another number to the right of 3, and when we do that, we see the first derivative is positive. So this part there is perhaps what we're used to. Well, we're going to do the same thing with the second derivative. Now, the second derivative is 6 times x minus 1. What's really important to note here, though, is we're going to put this number line right underneath the first derivative number line. So the second derivative number line is right underneath the first one. And we line up these x values with integrity. So if negative 1 is here and positive 3 is here, we're going to make sure that we put positive 1, which is the key number for the second derivative equaling 0, in between those two, so we maintain some integrity with the number lines, because in a sense they're all one number line, but we want to separate them out for purposes of our distinct interval testings. So 6 times x minus 1 is equal to 0. We simply pick a number to the left of 1 and plug it into this expression. We get a negative value. And we pick a number to the right of 1 and plug it into this expression, and we get a positive value. Okay, now what we're going to do is we're going to say, when we're to the left of negative 1, that is when we've got a positive first derivative and a negative second derivative. Our curve is going to have to be increasing concave down. Then, to the in between negative 1 and positive 1, we're going to have a negative first derivative and a negative second derivative. That's when we've got a decreasing concave down function. So our curve will have that shape there. Now, in between 1 and 3, we're going to have a negative first derivative and a positive second derivative. That's when our curve is decreasing concave up. And finally, to the right of 3, we're going to have a positive first derivative and a positive second derivative. That's when we're increasing and concave up. So we kind of have an idea, a better idea now what the shape of the curve will look like. Well, we need some key values. So what we're going to do is we're going to, we have the critical values, but we want to know what the points are themselves. So at x equals -1, we're going to plug that into our expression for y and figure out what y equals, and we get 15. When x equals +1, our y value will be -1, and when x equals +3, our y value will be -17. Now you see the curve there, but I want to point something out that's really important. We'll take our point at -1, 15, and let's say it's there. And then we'll take our point at 1, -1, and let's say it's there. And our point at 3, -17, and let's say it's there. Now, if you recall from the previous slide, I'm going to direct your attention to the shapes of the curves where I'm circling here. Directing your attention to there and bringing it to the next slide, we want to make sure that this portion of the curve that I just drew is increasing concave down, and then the next portion of the curve should be decreasing concave down. Now here's where I'm going to point something out, and I might not be doing it justice with my sketching abilities right here, but I'm trying to indicate to you that right now the tangent line should be above the curve at all of these points. I realize right here it sort of looks like I'm failing the vertical line test, but this pen isn't the easiest always to write with. Now, to the right of that point, we want to become decreasing concave up. What needs to happen there is the tangent line needs to switch sides. So on one side of that point of inflection, which is the point 1, -1, we want our tangent line to be on one side of the curve, but on the other side, we want our tangent line to be on the other side. It's important that you try to show that when you're doing the graphing um, on paper. You might have to erase it and go back and do it again. And then to the right of that last point, we want to be increasing in concave up. And so our curve looks like that. So ideally, if this had been done a little bit better, and it's not always easy to do it here, but you'd want to see that on one side of that point of inflection, the tangent line was on one side, and on the other side of the point of inflection, the tangent line was on the other side. If you do it with pencil on a sheet of paper, it's a little bit easier to do it with a lot of care. Now, we want to now show what the function y equals x to the 1/3 will look like. Well, first thing we're going to do is we're going to find the first derivative. And the first derivative is going to be equal to 1 over 3 times x to the 1/3 quantity squared. Now, we're going to see that that first derivative is never equal to 0. It's impossible for this fraction to equal 0 because the numerator cannot equal 0. However, it is undefined when x is 0. If I let x equal 0, that denominator will equal 0. So it's undefined when x equals 0. Now, we're also going to find out what does the second derivative equal? Well, if the first derivative is equal to 1/3 x to the -2/3, the second derivative is -2/9 x to the -5/3, and this can be re-expressed as shown here, -2 over 9 times x to the 1/3 quantity to the 5. And for the same reasons as f prime of x never equaling 0, f prime prime of x can never equal 0 because the numerator is 2. But it is possible for f prime prime of x to be undefined, so that'll be when x is 0. So what we're going to do on the next slide is we're going to stack our number lines. We're going to have a y prime and a y prime prime, and we're going to do interval testing on both. Now, the only value that makes y prime either 0 or undefined is x equals 0. And the only value that makes y prime prime either 0 or undefined is x equals 0. So we're going to line them up, obviously, one on top of the other because we want the placements of the numbers to be consistent, one to the other. Okay, and now that's what we've done here. And now what we're going to do is just do some interval testing. If we pick a number to the left of 0, a negative value, and plug it in for x, the third root of that will be negative, but then when we square it, it'll be positive, and 1 over 3 times a positive will be positive. And when we let x be a number greater than 0, x to the 1/3 will be positive. When we square it, it'll be positive, and 1/3 times that positive will also be positive. Now the second derivative, when we let x be a number to the left of 0, x to the 1/3 will be negative. And when we raise that to the odd exponent of 5, it'll still be negative. But our numerator is also negative. So we'll have a negative over 9 times a negative, which will be positive. We'll have a positive second derivative. And then to the right of 0, if we let x be a number, let's say 100, 100 quantity to the 1/3 is a positive value. Raised to the exponent 5, that is a positive value. Multiplied by 9, it is a positive value. But remember, our numerator is negative, so we'll have a negative value. So to the left of 0, we're going to have a curve that's increasing because of the positive first derivative and concave up because of the positive second derivative. So it'll look like what you see here, increasing concave up. But then to the right of 0, we'll have a curve that's increasing concave down, and it'll look like what you see here, increasing and concave down. Okay? Now, we finally want to know, since the only key value for us was x equaling 0, we want to know what y equals. Well, the function was x to the 1/3, so y will be equal to 0. So the only key point that we know about is the point 0, 0, and we draw the curve that you see here. Now remember, if you accidentally make this go down, you'll lose marks because that curve never decreases, and we know that because our positive, our y prime, told us that our it's always positive. The first derivative is always positive, so it's always increasing. So you can't get sloppy with your graph, but you also can't get sloppy with your graph and make it look like it goes that way, because we see from our second derivative that to the right of 0, we should always be concave down. And if you accidentally flare it out a bit, that's concave up, and you can't do that. And similarly, we can't get lazy and just let it kind of be a constant slope. That wouldn't be appropriate either. So you kind of have to take a little bit of care and concern when you're drawing these graphs to make sure you're doing respect to the concavity. In this question, this is an algebra question, no graphing required. They want us to determine any points of inflection on this curve. Well, to determine a point of inflection means we're going to let the first derivative equal to 0. So if f of x is x squared plus 3 to the negative 1, then f prime of x will be negative 2x times x squared plus 3 quantity to the negative 2. So this is what f prime of x is equal to, and we'll expand it out to look like this for a moment. Now, when we go to determine the second derivative, we're going to say, now this is going to look a little bit weird, but I'm going to use this version of the first derivative a little bit, and I'm going to use this version of the first derivative a little bit. Remember, they're equal to each other, so I can use either one. When I go to find the second derivative, I'm going to say it's low, d high. So I get x to the 4 plus 6x squared plus 9 times negative 2 minus high, d low, and again, that'll be 4x cubed plus 12x over low, low. And to do that, I'm just going to go back and recall that x to the 4 plus 6x squared plus 9 is really x squared plus 3 quantity squared. So I'll let that be the denominator, and I'll say that x squared plus 3 quantity squared in order to make it low, low is actually x squared plus 3 quantity to the 4. And I'll get this expression right here. Okay, now we're going to simplify this a little bit, that numerator on the next slide. And when we simplify that numerator, we get 6x to the 4 plus 12x squared minus 18. Factoring out a 6, we get that's equal to 6 times x to the 4 plus 2x squared minus 3. Well, it's not too tough from here to actually factor this out a bit. You can factor a trinomial when all of the exponents are even much of the time. So we have an exponent of 4, an exponent of 2, and an exponent of 0. So if this trinomial right there had been x squared plus 2x minus 3, I think most of us would say pretty easily that's x plus 3 times x minus 1. Well, since it's x to the 4 and 2x squared and 3, we can call that x squared plus 3 and x squared minus 1. So that's what we show in this line right here. And what's the point of showing that? Well, we have a factor of x squared plus 3 in the numerator, and we've got 4 of those in the denominator, so we can re-express that this way. Now, you might be saying to yourself, is it possible for us here to be crossing out a 0 factor? And the answer is no. We're crossing out x squared plus 3's, but x squared plus 3 cannot equal 0, because if it did, x would be equaling plus or minus the square root of -3, and clearly that's not possible. So we can safely say that f prime prime of x is equal to 6 times the quantity x squared minus 1 over x squared plus 3 quantity cubed. And we're going to factor the numerator, make it 6 times x minus 1 times x plus 1. Now, for the reasons we just said a minute ago, it's not possible for x squared plus 3 to equal 0. So there's not going to be any restrictions. And so the denominator cannot equal 0. We're not going to have to consider any points where f prime prime of x is undefined. We're just going to consider points where f prime prime of x is equal to 0. And so letting f prime prime of x equals 0 means x is 1 or x is -1. At x equals 1, our y coordinate, going back to the original expression, which is 1 over x squared plus 3, if we let x equal -1, y will be a quarter, and we'll get the point -1, comma, a quarter. And if x is equal to +1, y will equal a quarter again, and we'll get a point of inflection there as well. So those 2 points that exist on the curve and at which the second derivative is 0 are the points shown at the bottom in red. Now we're going to determine intervals of concavity for that particular function. So we saw in the last solution that when f of x is equal to 1 over x squared plus 3, f prime prime of x is equal to 6 times x minus 1 times x plus 1 over x squared plus 3 quantity cubed. The denominator will always be positive here. And so for our numerator, we can let x be any number to the left of -1. And when we plug a value of x into the left of -1, say for instance -2, we end up with a positive numerator over a positive denominator, so our second derivative is positive. When we sub in a value for x in between 1 and -1, we get a negative numerator over a positive denominator, so our second derivative is negative. And then to the right of 1, we get a positive first derivative. So we can say that our intervals of concavity will be that the function is concave up when x is less than 1 or x is greater than 1. Again, that's concave up is where our second derivative is positive. And we can say the function is concave down in between when the second derivative is negative. And if we want to show that in interval notation, we can show it in interval notation like this. And if we want to show the concave down in interval notation, we can show it in interval notation like that.